one thing to remember with clamp-on test instruments is that they're really good at measuring very low resistances, because what is low resistance when we throw Ohm's law at it? There's a decent amount of current there, right? So there's a
Yep.
decent amount of test current. As we go higher in resistance, now the instrument, because this is a current measuring device, and high resistance here, let's say, is going to be greater than 1,000 ohms. The instrument begins to range different, and we'll see the instrument range 5, 10, 50, and 100 ohms. Now it becomes less accurate. So I wouldn't take a 25 kilo ohm resistor and put it in between a piece of wire and say, hey, this thing works great. Take a 5 ohm or a 25 ohm or a 100 ohm resistor.
To that point, that goes right back into knowing your test set, right? Every ground test set you run into, what values are you looking for? Most of the time, you're looking for a number 25 ohms or less, right? I mean, it doesn't matter what you're testing. Now, if you're testing a single rod out of a big grid, you might get a 200 ohm rod or something like that. So, and then the old Biddles, you'd have to scale it down or whatever you're doing, right? So, but I mean, know what you're doing, know what you're testing. Don't, like you said, don't get a 25,000 ohm resistor. If anything, get a 100 ohm resistor and see if it measures it right. And at the end, you're not trying to perform calibration. Understand that. You're just trying to make sure that it performs properly. Let the calibration guy do his job, and then you do yours.
You mentioned function testing. I'll mention that, and I'm pretty sure every manufacturer has a version of this for their test instruments. And depending on the instrument too, there may be a different version of this. Like for us, for instance, for instruments that like the 6472 I have, these have internal bananas. So, or recessed bananas, I should say. This is a different calibration checker. We call it a calibration checker, but to your point, I call it a function check. Because it's not a calibration process. This has got a switch on it, and this will allow me just to change the resistance that the instrument's going to measure. I plug this in, it's color coded. I hit the test button, I should see the resistance that's on the box, or a number very, very close to it. If I see a number that's completely different, I'll obviously want to check this first, make sure this is working properly. The checker, and then I may have an issue with the instrument. I may need to set this aside until it's corrected, right? And rely on something that is working correctly. But function checks are critical. This is ideal, but this is not the only way to do it. To Tom's point, this can also be checked with a resistor and some leads. It's not super complex to visualize how this test instrument works, and then to perform some type of function check on it. So, you asked, what are some tips and tricks? I think the first tip that you could walk away from out of this conversation is to remember that the Earth is better described as a semiconductor than it is a conductor or an insulator, right? Because we tend to lump things into those groups. Now, I'm not talking like it's the same semiconductor that's in your phone, right? Because that's been highly processed and purified to be exactly, germanium, for instance, or some other type of semiconductive material. Here, we're talking about a mixture of either somewhat conductive, not conductive, or semiconductive materials that exist all layered together, right? We refer to it as the strata of the soil, but it's all very intermixed. And we've all seen this when we drive past a site that's been excavated. Remember that it's changing. It's going to change based on the temperature and the moisture content and all the other atmospheric conditions that will affect the soil. But as an average, the soil is about 1 billion times more resistive than copper. So you're dealing with a volume issue. I take a ground electrode and bond a copper conductor together to it, right? Generally speaking, very, very low resistance. Micro ohms should be, right? I stick this into the ground. Now I'm putting it into a material that be more like bonding it to a piece of wood or some other type. That may be a piece of wet wood, or I'm struggling to think of a material that is a better descriptor there. But it's not very conductive. So I have to have a lot of soil for it to do that same job as that conductor that's bonded to my ground electrode. Another way to kind of think about this for those of you that have gone through electrical training is when we use aluminum and aluminum conductors and bond those to copper conductors, we derate the copper, right? The copper is a better conductor than the aluminum. The ground is a very, very poor semiconductive material. And as I stick a ground electrode into it, I can expect that it's not going to be as conductive. Therefore, I need more soil. This explains partly why I need so much distance to perform fall of potential, right? Think of the shells or the amount of soil around the ground electrode as a series of resistors, right? The nearby soil has the highest impact because it's in intimate contact with the ground electrode. As I move further and further away, I see less and less resistance incurred. You can, if you've seen like a heat map for step and touch potential, it's exactly the same. It's the exact same principle that we're applying here for ground resistance testing. Why do I need to go so far away? I need to be outside of these shells or as far away as possible. Now, outside of these shells, even for a single ground electrode, is pretty far away. It's further than we actually do the testing. It's 200 feet or so. We need this spacing. We need this amount of space so we can find that equipotential or zero resistance connection where I'm no longer incurring a resistance. What is another principle about the Earth that is unique? It's infinite, essentially. It's a giant ball of dirt that we're standing on top of. Because it's so large, but it is so poorly conductive, I can place a remote Earth probe very, very far away and still be connected to the same thing, right? So I think one thing we struggle with when we look at how fall of potential is performed is we think in physical terms, right? We don't think electrically necessarily. We think of the geometry of the test and being exactly 100 feet away from a 10-foot driven electrode. Think more in the electrical principles of what you're working in. You're working with these shells that are essentially representative of a series of resistors, right? The further away I am, the more material I have introduced into the testing field between my two electrodes, the less resistance will be incurred the further it is I am away. I need to establish this remote Earth probe, the red lead or H, depending on the test instruments, usually always red, is going to be placed so far away that I am in an area that is close to zero resistance, right? It doesn't always have to be exactly zero, but it's very, very close. Other tips here are understanding how your instrument works. I think that's a fantastic one that Tom mentioned. Call the manufacturer. We have a ton of experience in talking to you and understanding what your use is, what your specific application is, and then suggesting to you the right instrument. Yes, we're a sales organization. No, we're not going to oversell you. I'm always going to give you a few examples of why I think this instrument could be better than that instrument, depending on your application, right? Tom and I were
3-pole to 4-pole, just like we talked about. Right?
3-pole to 4-pole, but even model to model, right? We have multiple 4-pole instruments, and there are some that are going to be better for your applications than others, depending on what it is you're testing, right? So the first question we're always going to ask is, what are you performing the test on? What measurement are you doing, right? What is the object that needs to be tested? What is the electrode system? Is it a set of 56 ground electrodes, or is it a single ground electrode? So understanding what it is that you're testing, how your test instrument operates, and then what your future uses may be, determine what it is that you need to do to apply to this test instrument, right? Lead length, it's a huge one. We were just talking about why remote Earth needs to be so far away. If you're testing something that's very large, it has a large horizontal component that has a ring of electrodes around it, or a grid of electrodes in the case of a substation, you're going to need to go much further to find that remote Earth. Because now I have more conductors in the ground, and they have a larger shell or set of shells, if you will, that I need to go further to find that remote Earth connection. So there's a lot that goes into this. It is a highly nuanced test setup that we can simplify for you if you'll just give us a call and give us the opportunity to do that for you.